This is Technical Module 2, Part 2. I'm Dan Gallagher, geologist with the California Department of Toxic Substances Control. In this portion of the presentation, I will be discussing the specifics in the draft guidance regarding sampling and screening of sites for vapor intrusion. The supplemental guidance provides additional specificity in regards to vapor intrusion relative to existing state guidance. So, I'll be discussing detailed data collection recommendations for vapor intrusion, which are currently lacking in existing state guidance. The supplemental guidance covers a number of topics. It discusses how to select buildings for vapor intrusion screening. Once a building is identified as potentially being at risk, it provides information on how to screen the building. The guidance talks about where and when to sample. The guidance also provides a framework for additional steps when a building fails the screening process. Generally, the guidance was written for the sampling and screening of a small residential or commercial building, but the guidance also talks about how to screen different types of buildings, such as large commercial buildings, at the end of the document. There are a number of topics that the supplemental guidance does not cover. The guidance does not discuss how to collect a soil gas sample. That topic is covered nicely in CalEPA's 2015 Soil Gas Advisory. The supplemental guidance does not discuss how to use mathematical models, such as the VaporFlex model or the Johnson and Ettinger model. Likewise, the supplemental guidance does not discuss how to set cleanup goals for a site. It only provides a framework for the development of screening levels. These are two very different topics. The guidance does not address how to remediate subsurface contamination, and it does not discuss how to mitigate vapor intrusion. For mitigation, please refer to DTSC's 2011 Mitigation Advisory and the San Francisco Water Board's 2019 fact sheet. The supplemental guidance provides a four-step process for the evaluation of vapor intrusion. This approach is modeled after the federal approach. The United States Environmental Protection Agency, in their 2015 guidance, has a bias for the sampling of indoor air early in the evaluation process, and the state of California has adopted this process. As the slide shows, step 1 is the prioritization of buildings and the selection of the sampling approach. Step 2 is using soil gas to screen buildings. If the soil gas data indicate a potential exposure, meaning the subsurface concentrations exceed a screening level, then indoor air sampling occurs in step 3. Then, with all the data, a risk management decision is made in step 4. The process can be linear, or steps can be skipped. For example, if a building is over known contamination, soil gas sampling should be skipped and practitioners should go right to indoor air testing. The supplemental guidance contains a decision framework for risk management that is used to evaluate the collected data. This table should look familiar to vapor intrusion practitioners in California. This is the same chart in DTSC's 2011 vapor intrusion guidance with one modification. In DTSC's 2011 guidance, risk management is based on the results of the indoor air sampling. This modified chart now integrates data from the subsurface into the risk management process. Both lines of evidence, indoor air and subsurface data, should be used to make risk management decisions. I'll talk more about this chart in a minute. As shown by this slide, when we sample indoor air, we are evaluating the risk to the current building occupants. The handful of indoor air samples that are collected only tell us about the current exposure to the building occupants. The future exposure in a building could be much different. If the building subject to testing changes in the future, the risk of exposure might also change. A number of things could happen to a building in the future, changing the exposure, such as changes in the heating and air conditioning systems, changes in the building due to remodeling, and the occurrence of additional foundation cracks in the future as the building ages. Older buildings are more susceptible to vapor intrusion as indicated by empirical data from schools in France. Accordingly, when making risk management decisions, the magnitude of the subsurface contamination needs to be incorporated into the decision framework. For example, things to be considered are the size of the soil gas plume, how elevated the vapor concentrations are, and the lifespan of the soil gas plume itself. Hence, large soil gas plumes with high concentrations that last a long time could potentially pose a long-term risk to a building as the building changes in the future. Now I want to walk through the stepwise process for evaluating a building for vapor intrusion. As with all potential exposure pathways, a conceptual site model should be developed for the building. Buildings under evaluation can be prioritized based on proximity and occupancy. Buildings near contamination would have a higher priority for assessment than buildings far from contaminant plumes. Likewise, building occupancy should also be considered. Buildings with low occupancy or no occupancy should be given lower priority. Furthermore, due to sewers acting as a potential vapor conduit, the sewer pathway should be integrated into the conceptual site model for the building. In step 1, there are two scenarios where soil gas sampling should be bypassed and practitioners should go straight to the sampling of indoor air. The first scenario is where the building is directly over a known contaminant release. For example, this is a scenario where release has occurred in floor drains or floor sumps in a building. The second scenario is where the vapor plume is connected to the building by the sewer. As shown in the figure, the sewer intersects the soil gas plume near the building. In these scenarios, indoor air sampling should occur rather than evaluating potential risk by the collection of subsurface samples. Practitioners should go straight to indoor air sampling in these scenarios. In step 2, soil gas samples are collected. Soil gas is a direct measurement of the media that can impact a building. Soil gas samples are preferred over soil samples, which are also known as soil matrix samples, for a number of reasons. By using soil gas samples, no partitioning assumptions are necessary as with soil samples. These partitioning assumptions introduce uncertainty into the risk assessment. Likewise, soil gas samples are preferred over groundwater samples for screening purposes. When using groundwater samples, assumptions must be made in regards to predicting contaminant transport over the groundwater's capillary fringe. These assumptions about the capillary fringe are alleviated by using soil gas samples. Again, soil samples or soil matrix samples should not be used for vapor intrusion evaluations. Soil tends to be heterogeneous, and soil gas samples are typically representative of a larger subsurface area than a soil sample. Furthermore, soil samples are subject to vapor loss even when using strict Method 5035 sampling procedures. Also, laboratory reporting limits for soil samples are typically higher than vapor intrusion screening levels. Hence, soil samples should not be used for vapor intrusion. Now I want to talk about the number of soil gas samples that are recommended for a vapor intrusion evaluation of a building. The supplemental guidance states that there should be one soil gas probe for each building, and that the probe should be installed between the building and the release area. Ideally, the soil gas probe should be installed as close as possible to the building under investigation. And when conducting a vapor intrusion assessment, the soil gas sampling for building exposure should be integrated into the overall investigation for a site. Accordingly, multiple soil gas probes may be needed to fully delineate subsurface contamination, in addition to the building-specific vapor probes. Hence, soil gas samples are generally collected for two reasons. They are used to evaluate vapor intrusion, and they are used to define the vertical and lateral extent of subsurface contamination. Concerning the depth of the building-specific vapor probe, the probe should be screened at two depths. The deeper screen on the probe should be located at the contaminant source, and the other screen should be located halfway between the source and the surface. As shown by the figure, which is taken from modeling conducted by US EPA, the shallower depth of the soil gas probe yields concentrations that are not indicative of the concentrations under the foundation. However, the deeper depth on the soil gas probe, pursuant to the figure, produces contaminant concentrations that are similar to those under the foundation. For this scenario, the contaminant source is relatively shallow, approximately 15 feet below surface grade. And it's important to remember that the underlying intent of a soil gas investigation for vapor intrusion is to determine the concentration of contaminants directly under the foundation. But what happens when contaminant sources are deep? Again, here's a figure from some modeling done by US EPA where the contaminant source is deep. This modeling figure indicates that the soil gas concentrations exterior to a building is equivalent to foundation conditions at about 15 feet below the building's foundation. Two scenarios are shown in the figure: a building with a basement and a building with a slab-on-grade foundation. Hence, under this scenario, the deepest screen for the building-specific vapor probe would be 15 feet for the slab-on-grade foundation and 20 feet for the building with a basement. However, deeper soil gas samples may be warranted if preferential pathways exist near or under the building. So to summarize, when contaminant sources are shallow, the deepest screen for a probe should be installed at the source. When contaminant sources are deep, the deepest screen for a probe should be installed 15 feet deeper than the building's foundation. And again, it's worth noting that vapor intrusion evaluations should be done in conjunction with full delineation of the subsurface plume. Full plume delineation is warranted so that an appropriate remedy can be selected for the site and, more specifically, the contaminant leaching to groundwater pathway can be evaluated. So let's look now at how to screen sites with soil gas data. The supplemental guidance contains a nice flow chart. Starting with your maximum soil gas concentration and an attenuation factor of 0.03, an estimate of the exposure risk is made. So with your two samples from your building-specific vapor probe, you determine if the concentrations exceed a risk of 1 in a million or a hazard index of 1. If so, you would proceed with indoor air testing, meaning the building is potentially at risk. If not, your building-specific vapor probe would be sampled again in a different season. Then, again, an estimate of the exposure risk is made with the second round of sampling results. If the concentrations exceed your risk threshold, indoor air testing is warranted. If not, the building would be classified as having a low priority. Accordingly, buildings are screened with a minimum of 4 soil gas samples. One building-specific probe is installed with 2 screens, and the probe is sampled twice before a building can be classified as low priority. The supplemental guidance provides a framework for indoor air sampling. Ideally, indoor air and the subslab should be sampled concurrently. The collection of subslab data will assist in the interpretation of the indoor air data. The supplemental guidance recommends the sampling of the occupied rooms, areas where the foundation is penetrated with utilities, and the areas of suspected highest subsurface concentration under the slab. 3 or more indoor air samples should be collected during each round of sampling. Outdoor air samples should be collected concurrently. Generally, the indoor air concentrations in a building can't be lower than the outdoor air concentrations, and this outdoor air information is needed in order to appropriately interpret the indoor air results. Also, vapor intrusion practitioners should consider the collection of additional lines of evidence during indoor air sampling, such as the collection of cross-foundation pressure measurements, information on the operation of the heating and air conditioning system or systems, and the collection of barometric pressure data. These additional lines of evidence will help with the interpretation of the indoor air results relative to the potential for vapor intrusion. Collection of indoor air data that's indicative of vapor intrusion is challenging. Indoor air contaminants display a large degree of temporal variability. This slide shows the variation in trichloroethylene concentrations in indoor air at a research home over contaminated groundwater near Hill Air Force Base in Utah. Arizona State University purchased this home and has conducted extensive indoor air testing within the structure. As you can see from the chart, indoor air has been tested numerous times on a daily basis over about a 3-year time period. The trichloroethylene concentrations in indoor air range by 3 orders of magnitude, and there's a seasonal variation to the indoor air concentrations. What this shows is that one sampling event will not potentially produce results that are indicative of long-term exposure conditions. Hence, numerous sampling events for a building are warranted in order to quantify the risk of exposure. To address temporal variability, numerous options are available. Practitioners can sample often, or they can sample continuously. Also, practitioners can get time-integrated samples over numerous days by using passive sampling techniques. The supplemental guidance discusses all 3 of these options. Now let's look at how to screen buildings with indoor air data. Again, the supplemental guidance contains a nice flow chart. Using your maximum indoor air concentration that's indicative of vapor intrusion, the exposure risk is estimated. If the indoor air concentrations exceed a risk of 1 in a million or a hazard index of 1, the exposure needs to be managed. If the indoor air concentrations are below screening levels, then the sampling should be repeated so that the temporal variability of the indoor air concentrations can be evaluated. This may require more than 2 sampling events. Sampling events should be done at different seasons. Also, practitioners should consider sampling the indoor air with the ventilation system off and with the ventilation system on. Again, this may require more than 2 sampling events. Upon collection of the indoor air data, it should be compared to screening levels to determine if exposure is occurring, and if so, the exposure needs to be managed. If all the indoor air testing yields results that are below screening levels, the building can be classified as having a low priority. Now I will return back to the risk management decision framework, which is step 4 in the process. This framework is meant to guide practitioners to an appropriate response action when buildings have concentrations that exceed screening levels due to vapor intrusion and when the subsurface soil gas also exceeds screening levels. There are 2 possible response actions. One option or outcome is when the exposure is within the risk management range, which is defined as a risk between a 1 in a million and 1 in 10,000 with a hazard index of less than or equal to 1. This is the yellow area in the chart. There are numerous response actions available to practitioners when buildings are within the risk management range. Buildings can be mitigated and/or the subsurface can be remediated to alleviate exposure. However, additional data collection may be warranted to further refine the risk estimates. This can be done through additional investigation and monitoring of either indoor air or soil gas or both. And other potential lines of evidence can be investigated. Likewise, institutional controls may be sufficient to manage the risk to building occupants. The second option or outcome is when the risk of indoor air and soil gas exceed 1 in 10,000 or when the hazard index is greater than 1. This is the red area on the chart. In these cases, building mitigation is warranted along with remediation of the subsurface contamination. This concludes the overview of the 4-step process within the supplemental guidance. Recalling, the supplemental guidance is a sampling and screening document. Remediation and mitigation are not addressed, as other state guidance documents are available for these issues. As I stated early in this presentation, the supplemental guidance was written for the sampling and screening of a small residential or commercial building. However, the guidance does describe how these concepts can be applied to other building types, such as large or multi-story buildings and buildings with crawl spaces. Crawl spaces can be sampled either during step 2 or step 3. Furthermore, the supplemental guidance also addresses buildings with above grade and below grade parking. The supplemental guidance also has 4 attachments. These attachments address petroleum vapor intrusion, the sampling of sewers, the screening of sites with groundwater data, and the uploading of vapor intrusion data into GeoTracker. I will now turn the presentation over to Cheryl Prowl, and she will talk about petroleum vapor intrusion, and I will return to talk about two of the attachments.
Thank you, Dan. When petroleum is the contaminant of concern, there are a few additional considerations. Petroleum vapor intrusion, also referred to as PVI, differs from chlorinated solvent vapor intrusion, or CVI, due to natural biodegradation of petroleum hydrocarbon vapors in the subsurface under oxygenated conditions, also known as bioattenuation. In the diagrams at the bottom left, the bioattenuation zone is shown in green. Petroleum typically releases and forms a non-aqueous phase liquid, which floats on the water table, and a portion can dissolve in groundwater. Vapors can partition from the residual product trapped in soil, floating product, or groundwater, and move through the soil. Oxygen moves downward from ambient air. Where both oxygen and petroleum vapor are present, naturally occurring microbes can break down the petroleum. This limits the movement of the petroleum vapor plume and decreases the likelihood of vapor intrusion. Typically, if there's enough separation between contamination and buildings, biodegradation will reliably occur and limit vapor intrusion. In contrast, the diagram at the bottom right shows a typical chlorinated solvent spill. Here, the vapor plume moves outward from residual product or contamination dissolved in groundwater, and there is no significant bioattenuation limiting its spread. It is conservative to assume that no biodegradation is occurring. The attachment gives advice for how to evaluate if biodegradation is occurring at a given site and how to adjust screening levels to account for the degradation. For any underground storage tank case, releases must be evaluated for vapor intrusion in accordance with State Water Board's Resolution 2012-62, the Low Threat UST Case Closure Policy. Policy is legally binding and must be followed. The proposed guidance should be viewed as recommendations and should never be used to avoid following the policy. The UST policy should also be followed for other petroleum releases that are small and share a similar conceptual model to a petroleum underground storage tank. However, for large or complex petroleum sites such as bulk fuel terminals, refineries, or manufactured gas plants, this supplemental guidance can be helpful. At these large sites, there may be portions of the site with insufficient biodegradation because of low oxygen, or there may not be adequate separation distance between the contamination and building foundations. In these cases, Attachment 1 can be followed, adding a site-specific biodegradation assessment to help evaluate whether the vapor intrusion pathway is complete. Thank you, and now I'll turn the presentation back over to Dan.
Attachment 2 in the supplemental guidance addresses sewers and their impact on indoor air quality. The attachment provides an overview of the sewer pathway and provides guidance on how to collect samples of sewer air. Recent studies have shown that organic vapors can move significant distances due to sewers. The transport of vapor due to sewers is not associated with the engineered backfill material that surrounds the sewer, but rather vapor transport occurs within the sewer pipe itself. As shown in the picture on the slide from Pinnell and others, in 2013, vapors enter the sewer due to contact with subsurface contaminated media, such as contaminated soil or contaminated groundwater. Vapors enter into the sewer due to cracks within the pipe and due to gaps within the construction joints. Vapors in sewers can travel significant distances by advection and diffusion, eventually entering into the airspace of buildings due to defective water traps in the plumbing and due to cracked pipes within the building itself. Vapor intrusion practitioners were sensitized to this issue by a study from Denmark. A 2017 study showed that 20% of the vapor intrusion cases in Denmark were attributable to the sewer pathway. Due to this occurrence and other documented cases, the sewer pathway was integrated into the supplemental guidance. Sewer sampling is not recommended in Step 2. the soil gas characterization step, but rather sewers should be evaluated potentially during the testing of indoor air. When testing indoor air, sewers should be considered for testing if there is evidence that the sewers intersect contaminated media. Furthermore, sewer sampling may be needed to diagnose unexpected indoor air results. For example, if a building is mitigated with a sub-slab depressurization system and the post-mitigation sampling still shows elevated indoor air concentrations, the sewer may be the source because sewers are not influenced by sub-slab depressurization. If sampling of a sewer is warranted at a vapor intrusion site, there are three options for the collection of the sample. As shown in the figure, sewer samples can be collected from access holes in maintenance covers that are in the street. They can be collected at sewer cleanouts on the wall of the building or at cleanouts that are a few feet from the building itself. Also, sewer samples can be collected from vents on the roof of the building. Additionally, there may be places inside the building itself where the samples can be collected, such as near the water traps at kitchen and bathroom sinks. The sampling of sewers is relatively simple. For street sampling, a metal rod and sampling tubing are needed. The tubing is secured to the metal rod and the metal rod is lowered down into the sewer through an opening in the maintenance cover. Ideally, samples should be collected a few feet above the liquid air interface in the sewer. The sampling tubing should be purged 3 times and the sample can be collected in either a SUMA canister or other appropriate container. Attachment 3 in the Supplemental Guidance addresses groundwater as a line of evidence in vapor intrusion evaluations. Groundwater data are not the preferred line of evidence for evaluating vapor intrusion because of the uncertainties associated with partitioning equations and uncertainty about vapor transport through the capillary fringe. Additionally, groundwater concentrations may not be reflective of vadose zone contamination. The direct measurement of soil gas concentrations bypasses these uncertainties, which is why soil gas is recommended as a preferred line of evidence in Step 2. Therefore, groundwater data should not be used as a sole line of evidence to support vapor intrusion decisions. However, groundwater data from the first water-bearing zone can be used as a supporting line of evidence to make inferences about potential vapor intrusion. Groundwater data may be useful when soil gas and indoor air cannot be sampled, such as for the open lot scenario where groundwater is shallow. Also, groundwater data can be used for determining the optimal location of soil gas probes. When using groundwater to estimate indoor air concentrations, partitioning equations must be used. This slide shows the conceptual approach for using groundwater as a line of evidence for predicting indoor air concentrations. The contaminant migration involves 2 steps. First, the vapor-forming compounds have to partition out of groundwater into the vapor phase. Second, the vapors have to migrate from the capillary fringe to the building. For this example, we're going to assume the tetrachloroethylene concentrations in shallowest groundwater are 6.4 micrograms per liter. The calculations will show that the corresponding indoor air concentrations for the tetrachloroethylene are 4.6 micrograms per cubic meter. A simple method for determining the soil gas vapor concentration right above the top of the groundwater is to use the Henry's Law constant. Groundwater concentrations are just multiplied by the unitless Henry's Law constant. As shown here, the tetrachloroethylene concentrations in groundwater of 6.4 micrograms per liter is multiplied by the Henry's Law constant of 0.72. This produces a theoretical soil gas concentration of 4.6 micrograms per liter right above the top of the groundwater. At this point, the units need to be converted. The concentration of 6.4 micrograms per liter needs to be multiplied by 1,000, producing a concentration of 4,600 micrograms per cubic meter. This completes the first step in the vapor migration calculation. To estimate the vapor transport through the vadose zone from the capillary fringe to the building, an attenuation factor is assumed for screening purposes. Accordingly, the soil gas vapor concentration of 4,600 micrograms per cubic meter is multiplied by the attenuation factor recommended in the supplemental guidance of 0.001. This yields an estimated indoor air concentration of 4.6 micrograms per cubic meter for tetrachloroethylene. Though conservative, this is an easy, straightforward way to estimate the vapor intrusion risk for a building over contaminated groundwater when there is no contaminant source within the vadose zone. There is one additional attachment in the supplemental guidance, Attachment 4, which addresses GeoTracker, and it will be discussed by Tina Uris of the State Water Resources Control Board. This concludes the presentation of Module 2, Part 2. Thank you.